We are discussing today about principal characteristic group frequencies. This is the continuation of previous classes. In this class we have to discuss about the characteristics absorption frequencies of various carbonyl compounds. Earlier classes we have discussed about the factors which influence the absorption frequencies of carbonyl compounds. Here we have to discuss about the what are the different types of characteristics absorption frequencies of carbonyl compounds. There are different carbonyl compounds, ketones, aldehydes, carboxylic acid, amides, esters, anhydrides, acyl halides, etc. First of all, we discuss about ketones. In ketones, the functional group is C double bond O. For a normal aliphatic ketone, the carbonyl stretching frequency is in the range 1720 to 1708 per centimeter. That is for normal carbonyl, that is the normal carbonyl stretching frequency 1720 to 1708 per centimeter. If this frequency lowers, if there is a conjugation, we have discussed earlier, that is in the classes, what are the factors which influence the carbonyl group frequency. There we have discussed about that the conjugation or conjugation with an aromatic ring causes lowering of carbonyl stretching frequency. Therefore, there is an alpha beta unsaturation near to this carbonyl group. This carbonyl stretching frequency is carbonyl stretching frequency decreases from 1720 to 1700 per centimeter, and also conjugation with a phenyl ring causes lowering of carbonyl stretching frequency, which is also in the range 1700 to 1680 per centimeter. Conjugation with the two aromatic ring, the value is carbonyl stretching frequency is 1670 to 1600 per centimeter. Again the value decreases due to this conjugation of two aromatic ring. In the case of cyclic ketones, again the frequency increases, carbonyl stretching frequency increases with a decreasing ring size. The reason is explained in earlier classes. Due to ring strain, this increasing frequency occurs due to the ring strain. There is, in addition to this carbonyl stretching frequency in ketones, there is another important frequency, that is bending frequency of carbonyl bending frequency, which appears in the region 1300 to 1100 per centimeter. Generally, that is in the case of ketones which show a very strong band for the C double bond O group, that appears in the range 1720 to 1708 per centimeter, which is the case for simple aliphatic ketones. This band is shifted to lower frequencies with the conjugation to a C double bond C or a phenyl group. An alpha halogen atom will shift the carbonyl frequency to a higher value. Ring strain moves the absorption to a higher frequency in the case of cyclic ketones. This is an example for an IR spectrum of a ketone. In this spectrum, the most important band is this carbonyl stretching frequency, which occurs in the region 1720 to 1720 in the 22, that is 1720 to 1708 per centimeter, that is this frequency. Second frequency we have noticed this is bending frequency, which is in the range 1300 to 1100 per centimeter. That is, these are the two important frequencies of a ketone. This frequency is aliphatic CH stretch, that is the CH3 CH stretch frequency is shown. These two bands shows the aliphatic CH stretch, and these two peaks are for aromatic C double bond C, and this peak shows the aromatic mono substitution is shown by these two peaks. This is a normal ER spectrum of a ketone. This is a alpha diketone, that is CH3 C double bond O C double bond O CH3. Here the ketone stretching CO stretching frequency is 1716 per centimeter. This is aromatic diketone. In this case, the stretching frequency is due to the presence of this aromatic ring. Again, carbonyl stretching frequency decreases, that is 1680 per centimeter. That is unconjugated diketones that have two carbonyl group. These are unconjugated diketone, two carbonyl groups adjacent to each other, shows one strong absorption peak at 1716 per centimeter. If the two carbonyl group are conjugated with the two aromatic rings, then the frequency again lowers and the value is 1680 per centimeter. In the case of beta diketone, that is 1,3 diketones, the carbonyl group is located at 1,3 positions with respect to each other, and in this case the beta diketone often exhibit a tautomerism or tautomerization, which is an so in solution it exhibits as the equilibrium mixture of these two structures. Therefore, the carbonyl group in the enol form appearing is at 1620 per centimeter, and it is in the case of normal ketone, that is it is 1723. There are two carbonyl frequencies, one is 723 per centimeter and other is 1706 per centimeter. This first one is due to symmetric stretch of carbonyl group and second one is due to asymmetric stretch of carbonyl group. That is, in enol isomer, enol tautomer, there is one more IR band, that is due to OH stretching frequency. This is in the range 3200 to 2400. Next is aldehydes. Aldehydes, the functional group is CHO and the carbonyl functional group CO stretch appears in the region. In the case of aldehyde, it is in the region 1440 to 1740 to 1725 per centimeter. Aldehyde show a very strong band for the carbonyl group in this region, that is 1740 to 1725 per centimeter for simple aliphatic aldehydes. The band is shifted to lower frequencies with conjugation to a C double bond C or conjugation to an phenyl group. A very important case in the case of IR spectrum of aldehyde is, that is, an important doublet is observed due to the CH stretch of aldehydic CH stretch in the region 2850 to 2750 per centimeter, that is 2860 to 2800 per centimeter. There is an important band is observed, that is due to aliphatic CH stretch. This is used for distinguishing aldehydes from ketones. This band is used for distinguishing from aldehydes and ketones. In the case of ketone, this band is absent. This is the spectrum of an aldehyde, that is CO stretch, which occurs in the region 1740 to 1720 per centimeter. This is normal aliphatic aldehyde. This is the CH stretch in aldehyde. This is absent in ketone. This frequency is present in both aldehydes and ketones, but this peak is absent in the case of ketones. This is another ketone with a conjugation of a double bond. Here the frequency reduces due to this conjugation, that this conjugation reduces the frequency 1740 to 1700, and the frequency, this is due to C double bond C conjugation. This frequency is due to C double bond C conjugation. This shows the CH stretching band of an aldehyde. Aldehydic CH stretch is shown this too. This is in the region 2800 to 2860 to 2800 per centimeter. These are the two important, this carbonyl band and this band are important for aldehydic group or for an aldehyde. Next one is carbonyl compound is carboxylic acid. You know that normal carboxylic acid, there is a carbonyl group and a OH group. This carbonyl carboxylic acid show very strong band, which is at band for the CO group in the region 1730 to 1700 per centimeter for simple aliphatic carboxylic acid. This exists in a dimeric form, normal state. This band is shifted to lower frequencies with the conjugation of a C double bond C or a phenyl group. In this case also, the frequency lowers due to the conjugation of C double bond C or a phenyl group. The OH stretch appears in the spectrum. There is an OH stretch which appears in the spectrum as a very broad band extending from 3400 to 2400 per centimeter. This broad band centers on about 3000 per centimeter. The most characteristic feature of the carboxylic acid spectrum is extremely broad OH absorption band occurring in the region 3400 to 2400 per centimeter. This band is attributed due to strong hydrogen bonding present in the dimer. There is also a CH stretch band in this case. This is the spectrum. This is the CH stretch is also present in OH. This is OH broadband, and this is the CH stretch frequency. This is carbonyl stretch frequency, which is 1730 to 1700 per centimeter. This is another band is important in the case of carboxylic acid, that is due to CO stretch, which occurs in the region 1300 to 1100 per centimeter. And these are the three important carbonyl frequencies: CO stretch, OH broadband, and this small sp3 CH stretch. These are the four important frequencies of a carboxylic acid IR spectrum.